Okay, so I wanted to go back and correct myself on one problem that we had. We talked about some of those transformer problems at the end of chapter 10, and I told you about the one that I was wrong, so I'm going to go back and get it. So if you're just coming in, there is a lab kit and a lab number 1 for each of you. If you um, there's a lab, and then somebody missed some pages, 11, 12, or 10, 11, 12. We should have 8 through 13, so there's 11, there's 12, 13.
How many pages total is it?
Huh?
How many pages total is it?
It's 8 through 14, I think. And it goes 8 through 14. So here's some more pages if you missed. Okay, 8. Okay, others. Yeah. So
It's 14 and there's 8.
it's maybe 14 the last page.
Yeah.
8 through 14. Does everybody have 8 through 14? Because there's some pages that might be, somebody's got some missing pages. Okay, there's some. You take a whole, you got a. Okay, so one of these, so you're all set. 8 through 14. All right. I don't staple them. I don't know if I should or not, but I don't. Okay, so we got a new look to our PDFs. I changed my web browser from Firefox to Brave, so for what it's worth. So down here, there was a problem that I totally muffed, and okay, so number 16, I explained it, and I think I messed it up. So anyway, let's do it again. Number 16, you have a 120 volt primary, and you have a 36 volt center tap secondary. And each half of those, this is 36 volts, this is total of 36 over here, 120 over there. And each half has its own 50 ohm load, okay? So there's 50 ohms here, there's 50 ohms here. So the 36 is split in half with 18 here and 18 here. Now, what is the I up here? We talked about that, and it was 18 divided by 50, or what? What is the I up here? 18 divided by 50 is what? It's 0.3, it's 360 milliamps. So I up here is 360 milliamps. So what is the I down here? It's 360 milliamps as well. Okay, so what is the total power? What is V times I over here? Well, it's this one plus this one. So what is it? It's 18. It's 2 times 18 times 0.36, because you've got two of them. You got this one and you got this one. So the power on the right side is equal to 2 times 18 times 0.36, or what? So it's 36 times 0.36 equals what? 12.96. So the power on the right side is equal to 12.96. 12.96 watts. So the power on the right has to equal 12.96 watts. So V times I over here has to equal 12.96 watts. So my V is 120. So what is my I of my primary? 12.96 divided by 120. So what's that? 0.108. Amp, or 108 milliamps. It's a strange one. That's not one that you would normally ask and get an answer to, but that's how that one's done. Okay? So this one is a little different from the other ones. The other ones basically is just, you get the number 17, for instance, you have a 12 to 1 step down, secondary is connected to a 10 ohm resistor. And again, let's do 15. So the number 15, this is the typical 15, is the typical question that I would ask. 6 to 1, if the primary is driven by 24 volts, so I've got a power supply over here, 24 volts, an AC. And transformers are very simple. This is a very simple problem. Okay, so you have a 6 to 1 step down, and then you have a 100 ohm. Over here, the load is 100 ohm. So the step down is from 24 to 4. 4 is the voltage. R is 100. So I is equal to V over R, or 4 divided by 100, or 40 milliamps. So that's my I in the secondary. Now, what is the I in the primary? Well, I showed you that the teeter-totter, 24 volts, 6 volts, so big, little, little, big. So this has got to be 40 milliamps. And this has got to be a sixth of that, 40 divided by 6, or what? I don't know what 40 divided by 6 is, but it's that 40 divided by 6 equals 20 divided by 3, or 6.67 milliamps. So I over here is 6.67 milliamps. Over here it's 40. That's the typical type of problem you'll get on transformers. Now 17 is the same thing, except for the fact that they don't give you a voltage on the primary. They just basically said, what is the primary resistance? Well, you don't have to find impedance. All you got to do is put a supply in there, and then you can find it based on
on, you sneak around at it. So basically assume something like 10 volts primary. 10 volts in the primary, and see what that gives you. So a 12 volt voltage drop, so I've got 10 volts over here, and I've got a 12 to 1. Or we could say it, well, let's make it really easy, make it 12 volts. I've got a 12 to 1, and so what would be over here? It'd be 1 volt. And if the secondary is connected to a 10 ohm load, so over here, I've got 1 volt, 10 ohms. What is it over here? Well, okay, what is I over here? It's 1 volt divided by 10 ohms, or it's 100 milliamps, right? It's 0.1. So I over here is equals 0.1 amp. So let's go back and do the same thing. 12 teeter-totter. 1, okay? 0.1 amp. So do I divide or do I multiply? I divide. So I say, okay, so I say now 0.1 divided by 12 is my current over here. So this is my I. So what is my R over here? R is equal to what? V equals IR, so R equals V over I, right? So it's equal to 12 over 0.1 divided by 12, or what? I don't know, you can figure that one out. Okay. You see how you do it? You don't have to know a formula for impedance. You just basically find V and I, and then you get V and I over here, and then you find R over here. So the primary impedance is this. Okay, so there's several people still coming in, and we still got plenty of the kits, and we still got plenty of the labs. So come up and get yourself a lab, or get yourself one of each. So this is the kit. This is the breadboard. And you take, not just the first page, you take all the pages, because there's take the whole thing. There's the whole thing right there. You're all set. We still got somebody missing pages 10, 11, and 13. Somebody's still missing a 10, 11, and 13. Check to see who's missing a 10, 11, and 13 out of your list. Somebody's 10, 11, and 13 is missing. You take the whole thing. So there's one of those. You get the 10, 11, 13. Still coming in, last kit, breadboard. Christmas. I want you to set up. I want you to have some good equipment. Those breadboards are extremely important because they do wear out. And if you wear yours out, you can get another one. But basically, the ones that we've got don't work well. All right? They're burned out. They've got old. I don't know which ones are good and which ones are bad. How's that? The ones you've got are good. They're high quality, and they may last you the whole full 4 years. And if they do, great. If they don't, you can get yourself another one. But basically, you get one from us, and those are good ones. So help yourself, protect them, all that good stuff. Don't lose them. They're yours. Okay? You can still do everything as a group of 2 or 3 if you want to do things. But one person out of the 2 or 3 of you has to bring your lab kit. Supposed to. Now we do have spares. If you're kit, we do have spares, but they're not as good as what you got. Okay. So I explained the bad, no. The whole, this is the whole one, this is the whole one. There you go, you got it, that's a 4. I didn't staple them. Take the whole thing. The whole thing. 8 through 14. I should do it this way. All right. Christmas. Lab kit, breadboard, and lab 1. Okay. Uh, Any questions anybody's got? And I went through the one problem that I messed up the other day, which was problem 16. So you can look at the tape and see how that one's done. But the ones that I would ask you are the ones that are, okay, so number 18 is the same thing. If you pick a voltage that, for the primary, that is conducive, like 10 or 1 or whatever, and then 1 to 5. So if you had 10 and you have 50 on the secondary, and then a 2 ohm resistor, and then the impedance is the same from the primary side, is just calculated by finding the primary voltage over the primary current. That's how it's done. That's the best way to do it. Or you can memorize the formulas and get messed up when what is the right thing and all that kind of stuff. This is the best way, and it works, and you don't have to remember any formulas. And anyway, so we're done with the DC book. Okay, moving on. Anybody have any questions? Moving on to the AC book, and they have a workbook with this, which I've never really looked at, but this guy is very thorough. A free book is a free book, but he does a good job, and he's very thorough, and he's into, you can tell he's into music and guitars and amplifiers and all that kind of stuff, which I'm not. But anyway, you can see some of his examples have to do with things that he's familiar with, and I'm glad, and but I don't pretend to go through all those examples. I kind of look at them and, yeah, they're nice, but I just want you to get the fundamentals down, and we'll get there. We'll get through this. Okay, so now we're talking about AC circuits. So we crossed over from the DC room into the AC room, and now you can legally say you're studying AC, what? Sinusoidal steady state analysis. So that's what we're doing. Good, better, and different. So this first chapter is just looking at the sinusoidal waveform. So after you do this chapter, which we'll probably get through just explaining it today, you'll be able to do the second part of that second lab. So I handed that lab out the other day, and I said, now this is just to hand in when you get through this other stuff. So today you should be able to do the rest of it. So that's, or maybe between today and Thursday. We'll see how it goes. So this is a sine wave. It goes up and it comes down, it comes back. Okay? Great. If you didn't know what that looked like before, that's what a sine wave looks like. Okay? That's what a cosine wave looks like. Now, here is a half frequency, here is a 1 frequency, and here is a 2 frequency of the same thing. Okay, so this is a slow boat, this is the medium guy, and this is, this is the slow boat, the medium guy, and the fast guy. Does everybody see that the blue one is faster than the green one, is faster than the red one? It goes faster. Per unit of time, it's twice, the blue one is twice as fast as the green one, is twice as fast as the red one. Now, how do you rationalize that? Well, how many times is it cut through the x-axis, through the 0 point, going up per unit of time? well, it cuts going up here, it cuts going up here, and it cuts going up here. So this one is twice the frequency of the green one, which cuts up here, and it cuts up again over here. So it's the frequency of the blue one is the frequency from here to here. So how do you measure frequency? I talk about it, but how fast does it go? How many times around does it go? So basically, I explain things in some weird ways sometimes, but how many of you have ever been to a dog track? Have you ever seen a dog race? Anybody? None of you? I've only done it once, but I did it. I saw a dog races. So they're down in Florida. So they do this for old people down in Florida. So I was a kid when I saw this. But what they actually do is they have a rabbit on a rail. It's not a real rabbit. It's a fake rabbit, but it's like a rabbit. And then they let these really fast dogs chase it. Okay, so the winning dog is the one that gets as close. But they never get to the rabbit. If they get to the rabbit, they mess up the dog, and the dog is never good as a racer anymore. So you can't let the dog get the rabbit. But they're going around and 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 around this racetrack. It's kind of fun. People get excited, they're betting and all that kind of stuff. I was 7 years old when I saw this. I wasn't betting anything. But anyway, so that's kind of how this goes. So you go around, and you go one time around, you go 2 times around. This is a slow boat. It only goes 1 time around. So this guy is twice as fast as this guy, who's twice as fast as this guy. Can everybody see you're going around a circle? This is going around. Now that's the half of the circle. This is the other half of the circle, and you're back to 0 again. So it's the same thing as going around a circle. So this would be considered 360 degrees. From here to here, you're going 360 degrees. Okay, going 360 degrees again. Here you're going the whole length, you're going 360 degrees. So from here, for the green one, from here to here is 360 degrees. From here to here, from here to here is 180 degrees. From here to here is 180 degrees. For the red one, he only makes it halfway around in this picture. So he's only made it 180 degrees from here to here. Okay? So you get the picture of dogs racing around a circle, and some of them are slow, some of them are fast, and some of them are in between. Now what we're going to get down to is that there is a lead and a lag dog. We're going to talk about that in a little bit. I'm going to talk about lead and lag, but we're not there yet. But now you're just talking about as you turn them around and all that kind of stuff. So you also have amplitude. Now the amplitude is the height of the signal. And when you talk about a signal, you do not necessarily talk about its amplitude, its peak amplitude. You talk about its RMS amplitude. Over here in the wall, I have a plug. Over here, there. So what is the amplitude of the signal coming out of this? It's 120 AC. 120 AC is the RMS. Now, what is the peak? RMS, okay, there's 2 numbers you need to remember, really 3. Electrical engineering technology, electrical engineering, square root of 2, square root of 3, and 746. Okay, now why do you need to remember the square root of 2? Because of today. Why do you need to remember the square root of 3? Because you go from single phase to 3 phase, you multiply everything times the square root of 3. What is 746? That's the conversion from watts to horsepower. Those are the only 3 numbers you need to remember. 7, square root of 2, square root of 3, and 746. And you don't need to remember those from me, but today you need to remember the square root of 2. What is the square root of 2? 1.414. Okay? What is the inverse of the square root of 2? 0.707. In my head, I've done it so many times, they roll. Okay? So I say 0.707, I mean 1 over the square root of 3, or square root of 2. When I say 1.414, I mean times the square root of 2.
So if you're converting from RMS to peak, you multiply by square root of 2. If you're converting from peak to RMS, you divide by the square root of 2, or multiply by 0.707. So again, I don't want to confuse you. I just want you to know that the peak value is not the value that most people recognize when they say 120. What is really the value coming out of the plug? 110, 115, something. Can be 120, can be 110. So what are you telling me? Transformers have losses. That's all I'm saying. So you can start at 120, and then they can lose a little bit, okay? You can lose nothing. You can lose a little bit. You can use, I don't know if 105 is you know, people get down to 105. I don't know. What do we usually use as a tripping point? If it's above 90, it's usually it usually works, okay, if it's above 90 volts, all right? If it's not above 90, it won't work. Most things have to be at least 90 volts to work, okay? But you supply 110, 115, 105, things tend to work, all right? Below 90, things start going haywire. Just general. So anyway, you have this maximum here. That's called the peak. Okay, so this signal has a peak that we usually don't call, we don't usually refer to it as that. We refer to it as, this is called V peak, but we usually say VRMS. When we're talking about voltage, we say VRMS, which is equal to V peak times 0.707, or V peak divided by square root of 2, or V peak divided by 1.414. Anyway, square root of 2. So VRMS is something a little bit less than, but we don't talk about it. We just talk about it. Why do we talk about VRMS? VRMS works like DC. Okay? So if I want to do power, I do V times I. That type of stuff, and you get the same, it works, the same thing, the same kind of things work with VRMS as do with DC. V times I. Power is equal to, for VRMS, power is equal to V times I. All right? And sometimes we just talk about voltage. I'll just do this. Here's my voltage supply, and it's 10 volts. Well, now is that, I'll say 10 V, and I'll do a little squiggly. Is that RMS or is that peak? We don't know. Unless they say little p there or that little VRMS. If they say it, then you know. But we don't know. It's assumed most of the time as RMS. That makes sense? Now you're getting a little bit scared of me, right? Because you say, no, he's saying a lot of stuff here all of a sudden, and I thought I knew about a sine wave, and I don't. They don't tell you every time. They don't give you a firm, it's RMS or it's peak. Please tell me RMS or peak. Please tell me, because I want to know. Sometimes in some of our labs, we get really down specific to exactly what it is, and you have to figure it out. Other times, not. No big deal. So some of our labs really get persnickety about this, and other times not. Now, if you want to look at all the parts and pieces of this waveform and all the things you can look at for the periodicity and all that kind of stuff, on the website, on my website, I have a hybrid PLC .org. They're gonna.
On the website, I have the book that is our, okay, so down here, key site oscilloscope manual. That's what we've got, by the way. We've got a key site. And there's the manual for it. It's 378 pages. It's a little daunting. But like most engineering books, if you want to find something specific, all you got to do is look at the index or look in the table of contents and you break it down and look and see what it is. So when it says stuff like, there are buttons on this thing that will give you all kinds of gizzies, all kinds of extra things. And, you know, I don't keep track of all this stuff, but right there is your key, okay? It's a key site, but right there is your book that tells you exactly how to look at a sine wave signal and analyze it for everything that there is in it, right here in this little book. Any questions about where to find stuff? This is the book to find it in, okay? So when you come up to me in lab, you say, now, so-and-so found all this stuff about under this button. How do you find that stuff? You know what I'm going to say? I have no clue, because I don't. But I had the smarts to at least bring up the book where it's at, and you can look in there and you can find it. It's there. It's all there, and it's all how every button on this oscilloscope. So you do lab 2, then you do lab 1, and you do lab 3. And lab 3 is just kind of an overview of this oscilloscope, okay? And then lab 4 actually starts into the regular labs. So you've got a little bit of time to kind of get used to it. Here's where you actually, during the commercials of the Super Bowl, no, you're not going to do this during the commercials of the Super Bowl, because they're more fun than the Super Bowl. But somewhere along in your next week or two, you're probably going to want to take a little bit of time and look through this book, okay? Peruse it. Don't memorize it. I'm never going to have a question on a test from this book, but, you know, in general, how do you read engineering books? Well, I read every line. No, you don't. You read them for what you need to get out of them. That's all you need to do, okay? And this is one of those books that's like that. But you do need to look at this book, okay? There's not going to be a question on a test from this book, but it is a good book to know that it's there. And why is it there? Because I don't have the time to memorize every button on that scope and help you with it. If I was a good lab tech, I probably would. I'm not. I get you started, I get you going, got your lab kit. I know what's important, but I do not have the time to basically understand and memorize every part and piece of this book. I do know that it's there, and you got access to it, and you can, the little buttons and what you do and how you do them for looking up the various parts of a sine wave are right here in this book explaining how to do it, okay? I'm not trying to duck my responsibilities to you, but I'm telling you that you get a lot further by looking in this than you will be by asking me. Some people just figure this stuff out. I don't. I struggle. But, you know, what I'm saying is that you need to know where your resources are. And that's an excellent resource. It's provided, it's there, it's free. It's just an excellent resource, okay? Now, what is this? That's an offset, right? What do you call that? They call it a DC offset. Is that good or bad? In general, DC offsets are bad, okay? So how would you show this on a drawing? In general, they're bad, and I don't really care whether they're good or bad. I'm just telling you that this is how you would show them on a drawing. You would have two power supplies. You would have the AC supply, and you'd have a DC supply, okay? So this would be the AC wiggle, and this would be the offset. I just call this the wiggle because it goes around 0, and this would be the DC offset, okay? So that's that. Have the same frequency, but have a DC offset. Now, why would DC offsets be bad? Because they could give you a bad signal. Most computer boards, I've told you this before, but most computer boards have capacitors but they're inputs for signals because they strip off that DC offset. The capacitor will strip that off. Now, what is this? Oh my goodness. Same frequency, but what? The red one is leading, the green one is leading the blue one. Does everybody see that? Now, these are the three dogs that are racing, and this one is the furthest ahead. This one's the next one, this is the third one. Okay, this could be the rabbit, the first dog, the second dog. Or this could be the rabbit's ahead of this one, and this could be the first dog, the second dog, and the third dog. They're going around, and they're going around, and they're going around. Now, this is assuming that they're always going to be the same frequency. And in case you wonder, dogs actually do, they change position. In the real world, they do change position. We're pretending that they're locked into a certain position and never change that. Frequencies never change. Once we get a frequency, one frequency in a circuit, that's the frequency. We do get phase shifts, but we don't get multiple frequencies, okay? We don't introduce a third frequency or a fourth frequency or this kind of thing and all that kind of stuff. We call them one frequency for a circuit, and it's either going to be leading or it's going to be lagging. Now, this one is, the green one is right on. This one is a lead, this one is a lag. Does everybody see that? Okay, this is where you actually are going to see those. You're going to say, now, how many degrees does this one lead this one? And you know what I'm going to tell you? Go back to the little book and find out where the button is that actually shows you how to do that. And it does. There's a button that exposes all that stuff. I don't know exactly where it's at, but I do know it's there. Some of you will find it. Some of you will say, now how would you get that? Well, there are oscilloscopes that don't actually show it. So basically, what is this? Well, each of these, from the green, from the 0 to the peak is 90 degrees. So basically you would say, okay, to the peak is from there to there. So from there to there is 90 degrees. So what percentage of that is from here to there or from here to there? And you say, well, it's about 30. It's about a third or whatever. And you'd say it's a 30-degree lag. And you can see that maybe, but this one is harder to see because it is so much ahead of this one. This is maybe about a 40 or 45-degree lead. Does everybody see that? Because from 0 to the peak is 90 degrees. Okay. It's kind of like, I got this little arm and I'm starting here and I'm saying go, and I come up to here, and at 90 degrees I'm at the peak of my thing. So here it's a counterclockwise. This race basically goes counterclockwise, okay? So I start at 0 and I come up here, and this is my 90 degrees, and that's that 90-degree mark right there. And I'm at 90 degrees. So I start my arm going, and then it's a little arrow that goes like this. It keeps moving this direction, and it goes to 90 degrees. Then it comes around to 180 degrees right here, and then it comes around to minus 90 degrees, and it comes back to 0, and I'm back. So basically, it's coming around like this. And you can see that dog. You can see him racing around that circle. There he is, okay? I can see it as a dog. Maybe you can't. Maybe that's not your way of looking at it, but I can see it as a dog at a dog track and racing around, and one being ahead of the other is a lead. The one that's behind is the lag, okay? So that's what you can think of it as. You can think of it as, how do you want to think of it? It's up to you. That's what's going on, okay? That's why these sine waves are like this, okay? So now we have all the parts and pieces of a sine wave. We have a DC offset, we have a peak, and we have a frequency, and we have an offset of theta. So theta is our lead or lag offset. Phase shift. This is called the phase shift. Theta is the phase shift. Okay? Now, how do we find the frequency? It's 2 pi times f is 1 over t. What is t? It's from when it does it to when it does it again, okay? There's no Pete's in here, are there? No. If this was Pete, this would be repeat, and this would be repeat again. Why is that? Because it's when it does it the same way. It's not when it cuts through. This would be half of it, but this would be the full cycle. So T is from here to here, okay? I explained that one time, and there was a guy named Pete in the and he didn't like the term. So I always ask. Pete and Repeat were in a boat. Pete fell out. Who's left? And he just grimaced because he had heard that joke 10 million times and he didn't like it. So anyway, so here it is again. So your time is from here to here, whatever that is, and that's this guy right here. So 2 pi f is 1 over that. So your frequency is that, whatever that is, okay? So your 2 pi f times t plus, so what does it take to go around one full time is what it basically says. One full lap is this 2 pi f times t is one full lap. Any questions? Oh, this is fun. Not. It's what it is, okay? So now how do you find t? Well, here's in milliseconds. So you find it by doing this. Say, okay, now here's where it happened. Here's where it happened again. It's 10 milliseconds. Notice it's not when it cuts through 0. It's when it cuts through in the positive direction again. So you look at this time right here. So it's t is 10 milliseconds. So frequency is 1 over t. I got that wrong. Sorry about that. 1 over t. F is 1 over t. Sorry about that. So we got, here is 1 where it cuts and cuts again. Now here's where it cuts here. So we got to go over to the same point where it cuts again, and the frequency here is 2 milliseconds. Okay. You see that? It's where it cuts to where it cuts the same way, same place again, and I go over here and it's 2 milliseconds. So t is 2 milliseconds, f is 1 over t, and away we go. All right, so finding f from t, t from f that's important. Also being able to look at an oscilloscope signal and being able to find its frequency. But again, like I said, you push the right button on that oscilloscope, and it'll tell you the frequency, it'll tell you the phase shift, it'll tell you everything you want to know about those signals. It'll tell you everything about it. So, this is not the one you have the one that's the book, okay? And you will have 2 waveforms, and you will see the phase shift, okay? And you will build circuits that will do this exact same thing. So what's the difference between sine and cosine? Okay. Well, sine starts at 0 and starts up. Cosine starts at the maximum, comes down. Derivative of cosine is sine. Derivative of sine is minus cosine. I remember that. I don't remember a lot, but I remember that, okay? Here's our RMS we just talked about. So again, most of the time they will give you, okay, now he does go through and he explains why RMS is important. The RMS describes the process of determining the effective value, or the value that when you multiply V times I, you get power. Okay, if peak or peak to peak is not specified, the measurement is assumed to be RMS. He says it right there. If you don't know, if it doesn't say, it's assumed to be RMS. Hopefully that doesn't upset you. Sometimes it'll be peak, sometimes it'll be RMS, but if they don't tell you, you can assume it to be RMS. And he does that, I think, pretty good. Any questions about that? So people are still coming in. I don't keep track. At the end of class, if you just have come in and you don't have a lab kit yet, or if you're too shy to get a lab kit, we got a free lab kit for you. At the end of class, you can come up and get a lab kit and a lab 1. So here is the proof that if you multiply how you get RMS, root mean square. And basic Fourier analysis. Fourier analysis is something that you wonder, what on earth are they going to come up with next, okay? Well, you can make a waveform, any waveform you want, out of just sine waves, okay? So if I had a square wave, I can make this out of sine waves. Why is that important? Well, you can do it. I mean, it's a fact. You can do that. And you can actually, I think they actually, I'm not sure how they make a square wave generator in a frequency generator, but I think they do this I think they actually do this. I'm not sure how they make a square wave. I don't know. I don't really care. I just know that they do, and I don't know exactly how they make a square wave. Okay, so I don't really know if that's the way that they make a square wave in a frequency generator or in a signal generator or not. But you can do it. Now, why is this important? Well, you have a series of signals, and you can say, oh, I can see how you can do this out of a bunch of signals, but it really doesn't matter until you get down to these higher frequencies and these signals right here. Okay, so there is a number that goes along with this, and this gets smaller and smaller as these frequencies get higher and higher. So see this frequency right here? It gets higher and higher as you get these values of these higher frequencies. The height of them gets smaller, but bless you, but the frequencies can get very, 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 very high. Okay. Now, I had a signal that was like this, okay? Now, I did not generate that signal from a bunch of sine waves, but in essence, what this is a bunch of sine waves. So what happens at high frequency? The impedance of a capacitor is 1 over, it's a value over C times F, okay? As the frequency gets higher, what happens to the impedance of a capacitor? If I have a number in here and it gets extremely large, okay, what happens to X sub C? Goes to 0, doesn't it? Correct? If the number goes to 0, what happens to I? If R goes to 0, I gets big. Okay? That makes sense? So I had these, and up in 2350, I had these tanks, tank over tank, and I got a bilge pump. And I was hitting them with a signal like this. And there's a little capacitor in that bilge pump that actually acts as kind of a smoothing device. If you were to run a bilge pump with 24-volt signal, a straight 24-volt signal, it'd work perfect. But because I hacked up the signal and varied it, it had these high frequencies, okay? You touch that stupid bilge pump and it's hot. I mean, it's so hot it'd burn your hand, except for the fact that it was in water. So if it ran out, if you ran the water down, stupid thing would get hot, really hot. Fill it back up with water, cools it back off. So would you ever do that in the real world? No, you wouldn't. You would not do that. Now, where else can that happen? What kind of signal do we hack up also besides little pulse? That's called a PWM signal, a pulse width modulated signal. Okay? Instead of having it on all the time, if you have it on half the time, it acts as if it's at half the value. Okay, so that's a pulse width modulated signal. That's called a PWM signal. If you do it like this, it's on 3/4 of the time. See, this would be 3/4 on and 1/4 off. This would be half on and half on. This would run at half speed. This would run at 3/4 speed. This would run at quarter speed. Okay? Those are PWM signals. But what other signal runs on a PWM? An inverter. Okay? Let's get down to it. Inverters run off PWM signals. That's how they do it. That's how you run it. That's how you run an AC motor is with an inverter. You take the signal, you take an AC signal, make it a DC signal, and then you hack it up, just like that, except for the fact that you make them really small. Okay? And guess what happens? That. So guess what you have to do? You have to put around an inverter to protect other circuits in your system. You have to put transformers that act like chokes. In other words, they smooth that all out and they don't let those high frequency signals go through. So you say, why are we talking about high frequency signals right now, except for the fact that they're real world, and you have to put these, they call them a choke, or you have to, every time you have an inverter, you have to do that. You have to, and they put them inside the inverter itself, so you don't have to worry about it. If you don't put that in the inverter, or buy it separately and put it outside the inverter, you get this all over the place. You get hot spots, you get circuits that won't work. So again, you may not worry at all about this. You say, well, that's nice, that's kind of a neat thing, isn't it? No, that's bad. Okay? So I also worked on a project long time ago, that we took the Fourier, they called it FFT, fast Fourier transform of a signal, and looked at the frequencies of the signal on, you probably would never guess this, but a field artillery generator for the Army. You say, why would you ever do that? Because the Army wanted to find out when generators for their field artillery pieces would go bad. It's no good to put a cannon out in the field if it doesn't have a generator next to it. Why? Because they use electricity to make the thing move. And if you can't move it, it's dead. It won't. It's too big to manually crank. You have to use a motor to crank it around to make it sure. So it's going to shoot in the right direction, okay? Everybody follow that? You got to have electricity. You got to have a generator to do that, because you don't have three-phase out there in your battlefield. So you have to pull a generator along with your artillery piece. And if a generator starts to go bad, what happens to your artillery? It doesn't work. So they were wanting to do this to bring in, so they bring in the generators, and they would put this tester on them, and they would analyze to see if these signals start to get big, these high frequency ones, not the low frequency, but the high frequencies, if they start to grow, you've got a problem, okay? Another place that they are interested in those high frequency signals is motors in general in factories. So they put an accelerometer on the motor. What's an accelerometer? It reads acceleration, gives you a little voltage out for acceleration. So as it jiggles, as it vibrates, it gives you a voltage, okay? That's what an accelerometer does. If something is jiggling, so the high frequency jiggles, the high frequency movement, the high frequency vibrations will show up, and they will discover which of those high frequency gyrations cause bearings to go bad. So you can predict when a bearing goes bad in a motor. So is this important? Yeah. It anticipates when field artillery pieces go bad. It anticipates when motors in whatever's go bad, it anticipates when a lab that we have, or why a little bilge pump heats up in our lab, so you can't touch it. So anyway, it has there's interesting implications about this little thing, and it's not like you have to go around and be searching for everything about it, but if you see the word FFT, fast Fourier transform, don't ignore it and say, that's for somebody else. No. It's for you. It is something that you need to know about, and you need to know that it exists, okay? Fast Fourier transforms. They exist. Now, when we did the thing with the when I did the thing with the field artillery pieces, we didn't have FFTs. That was a big Hewlett-Packard computer, mainframe Hewlett-Packard computer that did that analysis. We didn't have FFTs. Now we got FFTs, fast Fourier transform. It's on an oscilloscope. Some oscilloscopes actually do FFTs. So you can do that, and you can see where the frequencies are. So basically, what is an FFT? It shows you where the frequencies are of that signal. It shows you all the frequencies of that signal. It'll tell you which ones, and it'll show you when the ones that are bad are growing. Okay, so this is, I talked to you about that arrow. And there it is. Now we freeze it in time. We don't say it's constantly moving, even though it is constantly moving. We freeze it in time. So this is a leading one. This is right on, and this is a lagging one. We call these things phasers. I know that other people have called things phasers and all that kind of stuff, and Star Wars called things phasers and all that kind of stuff. We were the first to call things phasers, okay? So electrical people were the first people to call those things phasers, and that's a phaser, okay? It's not a phaser gun, it's a phaser, okay? And with that, we define everything about that signal. What does it not tell you? It doesn't tell you the frequency. I don't care what the frequency is. I do not care. I do not care. I just know that that's the signal that we're talking about right there, and that's an arrow. That's a phaser, and that is everything I need to know about that signal. Now, going along with it's the frequency, and by the way, it's the frequency of blah blah blah. Okay, that's how fast it's going around. I don't really care. I really don't care. Even though you may care a little bit, but it's not the big deal. But I basically say it's got a phaser, it's a magnitude, it's got an X and a Y direction, and I call this part of it, the real part, call this part the imaginary part. And this is the part that does not have the I, and this is the part that has the I, or we use the word J. Why do we use J? Because we reserve the term I for current. So I call it the real plus the J imaginary part, and that's how you define that thing. And I always get it back to polar format. So the answers that you give me on these problems, and there will be a multitude of problems through this book, it'll all be polar format. That's why the calculator. Okay, so you can flip back and forth. You know, I don't really care about this part. This is the theory behind it. This is you can, yep. When you took trigonometry, you learned all this stuff. You learned it in spades. As far as I'm concerned, all you got to do is describe it as real plus J imaginary or I imaginary, and you're in. That's all I care about. So again, the problems that you had doing the first part of that lab 2 are this, and that's all I want you to be able to do. And do that with that calculator. If you don't have that calculator, get one, because you will pay if you don't. Okay. Now here it gets down to what? The reactance through a capacitor and an inductor. Okay, so we have V V equals IR, right? Right? For capacitor. What do we have for capacitor and inductor? Now I'm talking about C's and L's, right? V equals for capacitor. This is for resistor. Voltage for resistor is equal to that. I times what? X sub C or X sub C equals minus it's equal to minus 1 over 2 pi f c times I, or times J. And that's equation 1.8. What's the voltage across an inductor? The I through it times X sub L, where X sub L is equal to J 2 pi f L. These are two things that you're going to have to just kind of learn. Now, why is that the case? Well, he explains it to you. Basically, ice and Eli, I equals C dV over dt. Voltage is equal to L di over dt. If you take the derivative of the sign, you get the, whatever, all that kind of stuff, and there it is. But this is the formula that you need to know. It's 1.8. This is 1.8. And for an inductor, it is 1.9. There they are. X sub L is a plus J, X sub C is a minus J, and there you have the rest of it. So there's your starting point for that. And that's it. Now all you got to do is what? Do the same circuits you did before, but now when you see an X or an, or what, now when you see an L or a C, what do? Substitute this or this, you're done. So that's all this course is about. Yes, that's all this course is about. That's exactly it. That's all this course does. Finding the I, finding the voltage, finding the this, finding the that, based on this and this as opposed to that. Oh, and by the way, you can have these mixed in with it. You can have these, and these all mixed in together. Now, why does this work? Why does this work? Because we talk about it as such. What did we say? Steady state. AC sinusoidal steady state analysis. Steady state means what? After it's been on for a while. We don't talk about the initial conditions. In other words, when you first turn a circuit on, what happens? We don't care. We say after it's been on for a while, what are the answers? And this is the way you do it. We don't care about the initial conditions. Okay, we don't care that maybe there was a spike or maybe that there was a this or there was a that or whatever. We just say now after the initial conditions, what happened in general after that? What happened? What do we see? And these are circuits that have been on for a while. We don't care that they just turned on. We just say after a while, what are they? And this is how it's done. Okay? So we can get away with this. We can get away with, these are second order differential equations. But as long as they're sine waves, and as long as we ignore the initial conditions, we can find what the long-term value of these is. And why is this important? Well, what is an inductor? What is a motor? It's an inductor. Okay? Why do we care about motors? Because they're practically everything that we do involves a motor of some kind, especially squirrel cage induction motors. So when we're looking at a motor circuit, what are we looking at? We're looking at an inductor. We're looking at a phase shift. Okay? We're looking at a shift in voltage, either current and voltage. Okay? When I look at a circuit, I say one is leading the other. Voltage is leading current, or current is leading voltage. And how do you know who's leading? Well, it's this guy right here, this ICE guy. In the capacitive circuit, who is leading? Well, I is before E or V in a capacitive circuit. So who's leading in a capacitive circuit? Who do you think is leading in that circuit right there? I, which is current. So if we have a capacitive circuit, who is leading? Well, it could be capacitive. It could be a little bit capacitive, or it could be a lot capacitive, right? We don't really care, but it's going to be something between 0 and 90 degrees. But what is it? I is leading C I is leading V in a capacitive circuit. In an inductive circuit, who's leading? Who's the head dog in an inductive circuit? Voltage. So if you're looking at a phase shift in a circuit, and you're saying, who's ahead? Is it V or I? You'd say, capacitive circuit is I, inductive circuit is voltage. So you can look at it. If you remember Eli and Ice, you kind of get that in your head. That's why I told you that back, whatever, and I told you that dumb story. You ever remember the dumb story? How did the guy become such a good runner in football? Ice. Okay, I told you that story for a reason. Not just because he's from the University of Illinois, although that. Red Grange. Anyway, so that's my story. Sticking to it. Eli Ice. Iceman. Anyway, that's that. Any questions about any of this stuff? So now you got the basic understanding, not only of what a sine wave is, but also what it does in a circuit. Okay? And now you've got an idea in your head how these circuits can be useful. So you kind of now have a little bit of an idea how to go about. So there's problems in this chapter. We got problems. And you also have problems in that lab number 2, that you can figure out how to do now. And that's the other part of lab number 2, is figure that out. And on Thursday, we'll do lab number 1 in class with your new lab kits. If it doesn't have the right resistors in there, we'll get the right resistors, we'll get the other components, but basically you got a breadboard. The reason for that lab kit is the breadboard. Okay, so if you lose everything else, don't lose a stupid breadboard. Keep it, and then that's yours, and that's the good part about that. Okay. Any questions anybody's got? If you missed early, you want a kit, there they are. If you know somebody that is not here today, but that needs a kit, I'll bring these kits back on Thursday, but also, if you know somebody that needs a kit, and also you owe me a quiz, right? I hate these because I have to grade them, but I know it's the only way to keep you, and also the problems at the end of the chapter, you need to be working on those. Hand those in as you get them done, because I definitely want to get those graded and back to you.